Welcome to my Godot FPS tutorial. In today's video, we will build a basic Sourcelike FPS movement script with Bhop and strafe. If you want to follow along, the starter project I'm using here, as well as all the source code, will be linked in the description. And without further ado, let's get started. So, to start, create a new scene and choose the type of other node. Then choose the character body 3D node. You'll see immediately it complains with a yellow triangle warning sign that it has no collision shape. So right click, add a child node, and search for collision shape 3D. After you've added the collision shape node, you'll need to assign an actual shape to it. We'll be using a capsule shape 3D, so select that. Once you've added a capsule shape, make sure to move the collision shape up so it's level with the ground. An easy way to do that is to check the height of the capsule shape and set the Y position of the collision shape to half of that. Then let's go ahead and save the scene. I'm going to call it FPS controller.tscn. And since I'm going to add a lot more after this tutorial, I'll make a folder for this character controller to organize everything a little bit better and put the scene file on there. Next, I want to add some meshes to our characters so we can see them a little bit better. So first off, I'm going to add a node 3D and rename it to world model. After that, I'm going to add a mesh instance 3D node to the world model node. And I'm going to add a capsule mesh to the mesh instance. This will help us see the character a little bit better in editor. And I'll move it up to the same position as the collision shape. Next, I'm going to add another node 3D, and I'm going to rename it to head. This will act as a pivot point for the camera 3D, so I'll add a camera 3D as a child of the head. And I'm going to move the Y position of the head node, not the camera node, but the head node up to 1.79 here. And this part is optional, but I'm also going to add some swag to the world model. I'm going to put these hair and glasses on him so we don't have to look at the default capsule the whole time, and also we'll know which way is forward more easily. These models are included in the starter project in the description. Make sure to put any models like this under the world model node, because one of the first things we're going to do is hide everything in the world model for the player's camera only. Now that we've got that all done, we are ready to start on the script. So right click the character body 3D node and add a new script. If it started you with a template script, you can delete everything except the ready, process, and physics process functions, because we're just going to be starting with those three empty functions for this tutorial. And make sure the process and physics process functions take delta as a parameter too. After that, right off the bat, we are going to set up some unique names for any objects of interest in our character body. I'm giving my world model, my head, and my camera 3D a unique name. These let us easily access the node and the script using a %sign. Then in ready, we'll add the code that hides anything in the world model from the player's camera. We are going to have a for loop which iterates over all children's in the world model node. All nodes have a find children function, and you can pass a asterisk or a star as the first argument, and the class type visual instance 3D as the second argument. This function will recursively search the entire node tree under world model and return any visual instance object. Then we can use the set layer mask value on the object and set the first layer to false and the second layer to true. That way, anything in the world model is going to be on the second visual layer. So we can just disable the second visual layer on the camera, and everything within that world model group is going to be hidden. To do this, select the camera 3D and unclick the 2 box under the cull mask. Next, let's drop our character body 3D into our scene and see if that all worked. I'm going to place our character in front of our mirror so we can see him. If you did it right, you'll be able to see your character in the mirror without your view being obstructed. If you did it wrong, it'll look something like this, where the glasses or maybe even the capsule could be obstructing your view. Back to the character script, I'm going to assume you got it right, and we are going to add in the mouse movement to look around. So first, to do that, I'm going to add in a variable using the export keyword. The export keyword allows us to use and set the variable on the character controller. So once you've added it and saved the script, you'll see it over to the right when you select the character body 3D And this is helpful for adding in adjustable variables to your character script. After that, you'll need to add the underscore unhandled input function, which takes one parameter, which is an event. And in that function, which is going to be called anytime there's an unhandled input, we are going to check if that event is a mouse button, which would be a mouse click. And if it is, then we'll set the mouse mode to captured, which means we'll be able to use the mouse to move the screen or the character's look direction around. And similarly, if the event is a UI underscore cancel action, which is a built-in keybind in Godot, usually bound to escape, then we will release the capture of the mouse and set its mouse mode back to visible. After that, if we have the mouse captured, then we can check if the event is a input event mouse motion. If it is, then we can use the mouse motion to move the camera and have our character look around. So we will multiply the event relative.x property by the look sensitivity and call the rotate y function, which is a built-in function on the character body 3D that rotates it around the y-axis, which would be left and right. And then similarly, we're going to do the same for the up and down looking, but this time we're going to rotate the camera 3D node on the x-axis. And remember, the % sign allows us to grab the camera node because we assigned it a unique name earlier. And we're going to use the negative event relative.y times the look sensitivity to rotate the camera 3D. And then finally, we are going to clamp the camera's rotation on the x-axis to -90 and 90. And this ensures you basically can't do backflips with your camera, and it's limited to just looking down to your feet or up at the sky, and you can't, bend over backwards and look behind you with the camera. Otherwise, it would just keep rotating forever. If you did all that right, you should now be able to start your project and then click to get the mouse captured, and then you'll be able to move around the camera using your mouse. Quick note, what is the point of using this unhandled input function? Well, let's say we use the regular input function instead, but we have a UI element. Well, you'll see we won't be able to properly interact with our UI because our character controller steals the input. The regular input function reacts to all input. However, if we use the unhandled input function, you'll see we can interact with the UI just fine. The character controller lets the UI handle the input event and only captures the mouse when the input isn't handled by the UI or anything else. Next, we'll be adding player movement. So the first thing you're going to want to do is go to Project Settings, Input Map, and then add the left, right, up, down, and jump actions. This allows us to bind action names and set them to be triggered by one or more types of keys. I want my movement to be used with WASD, so I'll be going with that. If you want to use a gamepad or controller for your character controller, this is also the time to add that. You can click the plus button, and any button you press will be recorded as bound to the action whenever you press it. So here I'm just using the analog stick on my gamepad and setting the actions as bound to the left, right, up, and down movement of the analog stick and the A button for jump on my controller. I'm also going to add one more action called sprint, and I'm going to bind it to my shift key. And I'm also going to bind it to the left analog stick clicking it down buttons. Then we are going to get to the movement code. So we're going to add a bunch more variables to set up here. You can copy the default values I have for mine. We're going to add the jump velocity variable with a default value of 6. I'm going to add a auto bhop variable and set that to true. Walk speed 7. Sprint speed 8.5. And then I'm going to add a non-export var wishter, and it's going to default to a vector 3 with all zeros in it. And the wishter is just going to be used to store the input direction we're pressing, because we might use it in multiple functions rather than just the physics process function. So above the physics process function, I'm going to add a couple more functions here. One is going to be handle ground physics, and one is going to be handle air physics. And I'm just going to start splitting these up pretty early because they might get a little bit more complex later on. So it's better to have them split up earlier rather than later. All right, now we will get to the movement code. So in physics process, I'm going to set an input dir variable, and I'm going to set that to the value of the input.getVector function with the 4 keybinds we set earlier, which are left, right, up, and down. Mine are WASD, and I'm going to normalize it. And then I'll set the actual wish direction function, which will be like the world direction that we want our character to move in based on the input direction. So we're putting the x of the input dir and the x of the world direction and the y into the z, since x and z are horizontal and the input direction is only a 2D up and down, left and right vector of which way we are pointing with the analog stick or our WASD keys. And here's a quick visual of the input.getVector function. As you can see, it basically takes whatever input keys you map to your left, right, up, and down, and it converts it into this 2D vector that's going to be pointing in the direction that you want to move. Note that it's in like a perfect circle. If you didn't know, that's what normalize does. It makes the vector always be of length 1. This is so if we press like forward and left at the same time, we don't go faster than if we were just pushing forward. And now there's this part right here as well, self.globaltransform.basis times the input direction vector. This is kind of a deep line. So basically what the basis is, it's basically just encompasses the rotation and scale of the object, and anything you multiply by a basis gets rotated and scaled to whatever the transform is that you are using. So in this context, it rotates the input direction so it's relative to the character, as you can see on the screen. And so if we delete this basis line, and this is from a prior example I made, you'll see that the input direction is no longer rotated relative to the character. I'm just pressing W and now I'm pressing S, and it's just kind of going in the world forward or back direction. And it's like I can rotate the camera and it doesn't follow along. So that's what the basis does. If you want a more in-depth explanation of how transforms and the basis type works, you can check out this previous video I made, which does a deep dive on how it actually works under the hood and gives an explanation of matrices. But yeah, that's not necessary for this tutorial. The only thing you really have to know is that you can multiply a object's transform.basis by something. In this case, we're using a direction, and that applies the rotation and scale of the object to that vector. So in this case, we have our input direction, and so when we multiply it by the basis, it makes it relative to our character. So you can multiply any position, vector, or other basis by a basis, and you can get this effect. So yeah, like the comment says here, you might have a very slightly different form of this than mine. If your character is facing in a different direction, that's fine. You can just negate whichever ones you need, and it should work fine for you. And then we will add this code to call the ground and air physics function. So if it's on the floor, obviously we want to call the ground physics function with the delta parameter. And then we will also want to call the air physics function if it's not on the floor with the delta parameter. And then regardless of which we call, at the end of the physics process, we'll call the move and slide function, which will make the character body 3D move. And in the air physics function, we're going to open by setting the velocity.y minus equals the physics/3D/default gravity from the project settings function. And this will just grab whatever you have defined here in the physics project settings. And I'm going to change mine to 12 because I thought that felt better and more realistic for the gravity. And don't forget to multiply the subtraction of the gravity from the velocity by delta, because it's an acceleration. It's not just applying a pure velocity every frame. It would be dependent on how much time has passed. And yeah, if you don't know, delta is just the amount of seconds that has passed since the last physics or process frame. So it would usually be like 0.01 seconds or something like that. And so yeah, now we have a good amount of code set up, and we can actually get some very basic movement going pretty quickly. So here's an example where we're just setting the velocity.x to the wishdir.x times the walk speed, and same with the z. And then just with that, you should be able to get a very basic walking around and looking around movement script going. And if you did a good job following the tutorial so far, as it turns out, my controller movement is actually backwards. So as long as you did it right, yours should be wrong also, funnily enough. And yeah, you might have to swap it depending on which way your camera's looking or your character model is. But yeah, we got a basic movement script going, so there you go. And another quick add here just to start building up functionality, we can also put a input.isAction just pressed for our jump keybind under the same isOnFloor that the ground physics is. And if so, then we set the velocity.y to the jump velocity. And now we can jump around, and gravity will be applied when we're not on floor in the air physics function. And another thing I'm going to add here is a designated getMoveSpeed function. And this will return our sprinting speed if we are sprinting and our walking speed otherwise. This is a little bit more robust, and now in ground physics and anywhere else we happen to use it, we can just call getMoveSpeed, and now our sprint will be enabled. Alright, and one of the next things we can do to add a little bit of juice to our character controller is to add a Headbob effect. So we're going to add a few variables at the top here, Headbob move amount. I'm going to set mine to 0.06. This is going to be how much it sways side to side or up and down slightly as we walk. And Headbob frequency, which is going to control how fast it moves side to side or up and down. And then we'll have a variable Headbob time, which keeps track of the basically the time along the up and down or side to side wave function. And then we'll add a function called Headbob effect, and it will take the delta parameter. And within the function here, I will, every frame, we're going to call this, so we'll add to the Headbob time the delta, which is the amount of time passed, multiplied by our current character velocity and the length of the velocity. So that's going to be the absolute velocity rather than just the velocity in the X, Y, or Z directions. So that'll make it so the faster we're moving, the faster our head is bobbing. And then we will set the camera 3D's transform.origin. And remember, this is where the fact that we had our head component actually moved Y, and the camera's position is still at 0, 0, 0. So the camera is going to pivot around the head node, and 0, 0, 0 will always center it back at the original head location. So we're going to exploit that here and move the camera pivoting around its origin point. So I'm going to set up a vector3 to set the camera's transform.origin, and setting the camera's transform.origin is the exact same as setting the camera's position, so you can do either one. And then we'll have this line here, and you can just copy this. I'll explain it in a second. It will take the cosine function, which is the built-in function if you've ever seen a sine wave or a cosine wave. They're almost the same thing. They look very similar. They're just offset slightly one from the other. So we'll take the cosine function, and then in the function, we will multiply it by the frequency of the Headbob times 0.5, and then multiply that by the amount we want the head to move. So this will control the side-to-side movement. And then the up and down movement is in the Y, so we'll have that not multiplied by 0.5 and basically the same thing, so it moves slightly more quickly up and down rather than side to side. And then go ahead and call the Headbob effect function with the delta parameter in the handle ground physics function. And if you go and save that, you should have your Headbob working now. And how this is working is pretty simple. Remember what a sine wave looks like if you remember your graphing calculator from math class, something like that. And this is what the sine and cosine waves look like, of course. We're just using this smooth up and down wave function with time to move the head up and down with time. Walking in a straight line while shooting, it's pretty cool that you can actually see the sine wave from the Headbob in the bullet pattern. One quick thing I want to mention here, when you see me using this : equals, what does that mean? Well, that's usually good practice. It basically sets the type of a variable in stone. So here's an example. This isn't actually relevant to the tutorial, but if we set ABC to a vector, then we reassign it to 5, a number, there's no error, but with the colon, that enforces the type as whatever it's initially set to. So just a little safety mechanism to help you prevent errors in your code. And one more thing I still need to add here to use this auto bhop variable, I'm going to add a clause to this if function. So if auto bhop is true and is action pressed jump, then we'll allow a jump. So the difference here is that with auto bhop enabled, you can just hold down jump and it will automatically jump as soon as you hit the ground. With auto bhop off now, it'll force you to repress jump every time. You can't just hold it and keep jumping. That's the difference between the is action just pressed and the is action pressed functions. And a good time to mention this little quirk of the is action just press function. Here I'm in the Godot engine source code. Cool thing about using an open source engine. Anyone could just look at the source code if you're curious about how it works. You'll notice in the is action just pressed, there's an if statement that checks whether we're currently in the physics frame. So it checks whether it's being called from the physics frame or the process function, the physics process or the regular process. And so it will be, if it was just pressed since the last frame of whichever one you're in, it's context based on how it works. And now I want my character controller to work with the gamepad or any controller anyone wants to use. So I'm going to add these input functions: look left, look right, look up, and look down. And I'm going to bind these input functions just like before, but to the right analog stick on my gamepad. And then if you don't want to use gamepads with your controller, you probably don't need to add this, but I'm going to add it to mine, and this is how you do it. And now I'm going to add a controller look sensitivity variable similar to the mouse sensitivity. Mine is 0.05. And I'm going to add a handle controller look input function. And you'll see I'm going to set this up with a target look, and I'm getting the input vector of the look left, right, down, and up function similar to the movement vector, but this time for the controller look vector, or the controller look direction from the controller analog stick. And you probably don't need this if you're not looking to smoothly interpolate the controller input, but this is just a personal preference. Mine felt a little bit better when I added a slight amount of smoothing to the controller input, so I'll show you how to do that optionally. So for now I'm just going to set the curve controller look to the target look. I'm going to rotate Y just like we did in the mouse input, but this time with the controller.x instead of the mouse movement x. Same thing with the camera 3D, looking up and down, and same thing with clamping the camera looking up and down so it can't look behind you and rotate forever. And then I'll be calling that within the process function with the delta parameter. And this will work just fine for looking around with the controller, but it might be a little bit hard to aim. Like if this was this is going to be a first-person shooter game, so at least on my controller, it's kind of hard to aim like this, so I decided to add some movement smoothing to the controller look. And basically for that, we're just going to add a few lines here. We're going to have an if statement that if the target look length is less than the controller length, this will usually happen if if they're trying to stop looking to the left or right, they'll just stop moving the analog stick, so the length of the controller look vector will go to 0. So then just set that to the target look. Otherwise, like if they're trying to move quickly to the left or right, instead of setting it directly, I'm going to use the linearly interpolate function. LERP is what that stands for. And I will use 5 times the time, and maybe you could also change this to your liking as well. So it's basically going to smoothly interpolate towards over a short period of time to the desired look direction, or or clear controller look to the desired look direction, so it adds a small bit of smoothing to make it feel a little bit better, in my opinion. And yeah, now you might notice it just looks a tad smoother, and in my opinion it feels a little bit nicer, and it's a little bit easier to aim. Like if I'm trying to put that top ball there in the center of my screen, it's a little bit easier because there's a little bit of a slow acceleration when I start looking, but I can always get up to the speed that I want, but it makes it a little bit smoother. Now currently when you jump, you have no control in the air, so we're going to add that now, and we're going to follow the recipe of some really famous preceding games, including Quake, Half-Life, and Counter-Strike Source. So what I'm going to do here is add some variables, and this is a little bit of magic here. I mean, this is really just a recipe. I can try to explain what these are, but I don't know why exactly these variables make the controller feel so good, but they do. They've been, tried and tested, and these are the values that I have found to work. You probably try, adjusting these for yourself, and you might find better values for how it feels for you. But you're going to need these three values: air cap, air accel, and air move speed. And specifically for surf, which I'm also going to do in this tutorial, these are important to have. So once you have those variables, go down to your handle air physics function, and this is really just a bit of magic. We are just following like the classic movement recipe of how air physics works in this genre of games. I think this was originally in Quake, or maybe even before that in Doom or something. This is a very specific recipe that uses a dot product in the direction that the player wants to move. So I want to quickly review what the dot product actually is, because we're about to use it a lot in the next few functions here. Essentially, it is a measure of how much two vectors are pointing in the same direction. Here we have two vectors of length 1. If the two vectors are pointing in the exact same direction, the dot product will be 1. If the two vectors are perpendicular to each other, the dot product will be 0. And if they're facing exactly opposite from each other, it will be -1. And if it's anywhere in between, it will be something in between either of those values. So if it's almost aligned, it's going to be closer to 1. If it's almost perpendicular, it's going to be close to 0. And this is essentially a way that we can use as a tool to measure how much one vector is pointing in the same direction as another vector. If either of the vectors are not length 1, the resulting dot product will be scaled by the length of both of the vectors. So you can imagine if the vector A is the player's current velocity and the vector B is the player's input direction, we can use this to calculate how fast the player is already moving in the input direction. But even if the player is moving quickly, if we set it to length 2, they will still be basically moving at 0 speed in the direction of the input vector. And when we say dot product, we really just mean multiplying each of the x components and each of the y components of each of the vectors, and then adding up the resulting values of each of those multiplications. Why this turns out to be a measure of how much the vectors are pointing in the same direction is a question for another video, but now you understand the dot product, hopefully. And so we're going to use that premise in our first line here in the handle air physics function. So we take the dot product of the current velocity of the player with the wish direction that they want to move in. This lets us know how fast the player is already moving in the current direction that they want to move in. And then in this next line here, we're basically going to get a maximum speed cap that we could possibly move them to. So this will depend on what you set for air move speed and air cap. And the cap speed will be 0 if the player is not pressing anything, because it gets multiplied by the wish direction, which would be 0 in that case. For the next part here, we are going to take the capped speed and subtract the current speed in the wish dir from that. This checks how much speed we can add before they hit the max speed cap we set. And notice we're only checking how fast the player is moving in the desired input direction. So they could be going 1,000,000 miles per hour forward, But if they try to press left or right, they're going 0 miles per hour left and right. So we'll still be able to increase their speed even if they're going extremely fast already. This is what allows for the iconic Source Engine and Quake movement that allows for things like bunny hopping and surf. This all hinges on this ability to strafe move left and right in the air and continually gain speed basically forever. And then for the next part, we will add an if statement, which checks if we have any speed to add until we hit the capped speed we decided on above. Then we calculate this accel speed value from the air accel, air move speed variables multiplied with delta. This is going to be multiplied with the wish direction for how much speed to add to the player's current velocity. We also do a min with the add speed till cap, and this is going to make sure we're not increasing the player's velocity past the speed cap. And it seemed to work fine without that part. I didn't notice any difference really, but this is all just sticking to the classic Source Engine or Quake style movement recipe so we can get that really nice Source Engine movement feeling. And that's all you need in your air physics function for now. And if your gamer senses are really sharp here, you're going to see we have this CSS style kind of air control. We still don't have Bhop, so it's a little bit weird when you hit the ground, but you could see you can kind of strafe or like tilt your camera while pressing A or D mid-air. And you're also able to like jump, press S in the air, and then it'll stop you kind of over the spot you're at. But this is probably going to feel really good if you played a lot of Source games before. Now, if you're like me and you played a lot of CSS, after feeling that Sourcelike air movement, you're probably eager to get the Bhop and the proper ground movement in, so you don't just like completely stop when you hit the ground and keep the momentum. So we're going to add the ground movement settings in. So first I'm just going to move the walk speed and sprint speed under this ground movement settings to keep it organized. Then we're going to add a ground accel variable. We'll set that to 14. Ground decel is 10, and ground friction is 6. And these are just the values that I found to work for mine. You might change those three. Alright, now down in the ground physics function, we are going to replace the basic movement code we had earlier with just setting the velocity x and z directly. And this first half here is going to be very similar to the air physics code. We're going to do the same thing where we get the current speed in the wish direction and dot it with the current player's velocity. And then we'll do a very similar thing again where we set an add speed till cap function, which is basically the maximum speed we can add until we're at our speed limit. And that's going to be the player's get move speed function, so walking or sprinting speed, depending on if they have shift pressed. And same deal here, we're going to do an if statement if we have any speed to add till we meet the speed limit in the desired direction. And then we'll do this thing again where we get the accel speed by the ground accel times delta times the move speed, and making sure we don't add it past the cap by taking the minimum between the accel speed and the speed till the cap. And then we'll add to the velocity based on this accel speed, just like before, multiplied with the wish direction, so they won't move if they're not pressing anything. Up next, we are going to program in some friction. So we'll do a max, choose the maximum value between the current velocity and the ground decel. And my ground decel is set at 10, so basically unless the player is going to be moving really, really fast, it's going to use the ground decel value as the control. And then we set drop as the control multiplied by the ground friction times the delta, and this will be how much the velocity should drop each frame for the friction. And then we'll calculate a new speed variable just by getting the current absolute velocity subtracted by that drop value and making sure it is greater than or equal to 0 by maxing with 0. So we choose the maximum value between the two. That's what that function does, of course. And then if the current velocity is greater than 0, so if we're not stopped yet, we are going to apply the friction while on the ground here. That if statement there also prevents dividing by 0 in this next statement here where we do new speed divided by equals the current velocity dot length. And now after that divided by equals part, new speed is basically like a ratio of how much slower the velocity should be for the new velocity after we apply the friction. And so then multiplying velocity by new speed will slow us down by the appropriate amount. And that's all we need for our ground physics function. And there you go. If you give that a try, you get some really awesome buttery feeling Bhop. It's especially nice with the auto Bhop option turned on. If you're any good at Bhop, if you played some Source games, TF2, Counter-Strike, or anything with Bhop in it, if you're good, you can probably gain some speed doing this. The concept is basically you can air strafe, and this is kind of like a bug almost, but it is a desirable bug for a lot of people. This has spawned like a whole like games just based off of this movement. I remember sitting in the Counter-Strike Source Bhop servers back in the day doing these obstacle courses with this and the surf servers. So it feels pretty awesome if you've played this exact genre of game before. And this is pretty nice to get the feeling in Godot. Up next, there's one last thing I want to add, and that is a surfing mechanic. So surfing in Source games hinges on this one function, clip velocity. So we're going to define a function used in air physics, and it's going to have 3 parameters: normal, overbounce, and it's also going to take the delta parameter. And we're going to use the dot product again here. The idea being that normal will be the wall normal passed in that we're currently sliding on. So the dot product with the current wall normal, which would be like pointing towards us, if we're pushing into the wall, that dot product would be negative. And multiplying it by overbounce, which by default, usually it's going to be 1. So this calculation is going to give us like how much velocity we need to back off the wall in the opposite direction of the normal. In Source games, this is how they prevented you from clipping into walls. So they basically pushed your velocity away from the wall if you're moving into it. This results in you smoothly sliding along walls if you're midair. And that's what will allow this surf mechanic to work. Next, we are going to check if the back off is greater than or equal to 0, which would mean that we're already moving away from the wall and we can just return. If we don't return, we are going to get this change variable, normal multiplied by the necessary back off velocity, and this is just going to give us a velocity to change the player's velocity by, which will prevent any movement towards the wall, and this results in us sliding along it. And then subtracting the change value from the current velocity value, we are pretty much good to go. Per the original recipe, I'm going to add this last part here where we have an adjust variable. And we basically just run the same thing twice. The idea is to make doubly sure that the player isn't still moving into the wall. And I'm not totally sure if this is necessary, but this was in the original Source clip velocity recipe. And that is all you need for your clip velocity function, which will allow you to surf on sloped surfaces that are steeper than is considered to be the floor. If you want to know what exact angle that is going to be set in your max floor angle variable on your character body 3D. And so finally, to complete this code in the handle air physics function, we're going to add an is on wall check, and if so, we'll call our clip velocity function. And what we have now will work for surfing, but I recommend adding another function to make it super buttery smooth and prevent any potential issues. This is something I found to work better. So we're going to add an isSurfaceToSteep function that takes in a surface normal, and then we are going to rotate an up vector towards max floor angle or by max floor angle. So it's basically tilting a directly up vector to the same angle as the maximum floor angle allowed to walk on. And we're taking a dot product with up, so we'll measure how far away that vector is from up. And then we do another dot product of the surface normal with up. And remember, the dot product is checking how closely aligned two vectors are. So we're saying which is more closely aligned with up, the max floor angle or the surface normal. And if the surface normal is less than this in terms of how closely aligned it is up, then that is going to mean it's too steep. So we return true for too steep. And we'll be able to use this in our handle air physics function to add another clause here in our if statement. And basically, we're going to swap, depending on if we are on a surface that's too steep, we're going to swap to the motion mode floating for the character body 3D. And I just noticed this prevents jittering and any glitches. And like on some ramps, if they're really steep, it'll just like, you'll just get stuck without this. So yeah, we're setting the motion mode to floating if the surface is too steep when we're on the wall. Otherwise, we set it back to grounded, which would be the default. And this bit of code here is a bit tricky. So when you're in the floating mode, there's no concept of the ground. So we'll be locked into air physics as long as we're in this floating mode. So whenever we hit a wall again, or the floor, when we hit the floor, it will be detected as a wall. So we'll go back here, and if the floor is not too steep, then we'll get set back to grounded mode. And I found this to work a lot better to smooth out the surf physics. And now that we have surf physics implemented, you're probably going to want a surf ramp. So an easy way to make that, you can add a path 3D to your scene. Then move the path 3D to the desired spot of the surf ramp. And then go into the aligned orthogonal view. And with the path 3D selected, you can click the tool icon with the plus button at the top, and you can add some points to it. Then that second icon there, if you press shift while that's selected, it allows you to bend the path into a smooth ramp type shape like this. Then you can add a CSG polygon 3D as a child of the path. And then in the settings of the CSG polygon 3D, you can set the mode to path. And then if you assign the path node to it, you'll see that it creates a polygon along this path. And you're probably also going to want to set the path local option to make it align perfectly with the path. Then you can delete one of the vertices of the default square polygon to make it a triangle, and move the middle one over to make it like a pyramid shape. And when you're creating these, it gets a little bit finicky if you're moving, especially the CSG polygon node. So I found it to work best to scale the actual path 3D node rather than the CSG box one. I also left the vertice numbers in the single digits because that was getting finicky as well when I changed those and then try to make it follow along the path. Then you can throw a texture on it, and it makes this weird pattern on one side by default, but I think it looks kind of cool, so I'm going to leave it like that. And to make it surfable, don't forget to select the use collision on the CSG polygon 3D so you can actually collide with it with your character body 3D. And then with that, everything is done, and you'll have this wonderful surfable ramp, which will feel very nice and familiar to you if you've done some CSS or any source engine game surfing. It's a lot of fun. If you have no idea how surf works and you're just following this tutorial just to get the character controller, I could try to explain it. You might as well look up a tutorial. It's kind of hard to get the hang of at first. Might be a whole separate tutorial to teach surf, honestly, but the basic premise is while you're sliding on the ramp, you don't press W, you only press A or D. You strafe into and towards the ramp. And yeah, that is the tutorial. I hope you enjoyed it, and I hope you found it helpful. I hope you have fun with and enjoy this character controller you made with me. And stay tuned for more parts of this because I'm going to be adding more features to this character controller. As a reminder, all the source code is available on the GitHub repo linked down below. If you have any questions, you can go ahead and leave them down below, and I'll do my best to answer. And thanks for watching.